Welcome to Cloud OnAir live webinars from Google Cloud. We're hosting webinars every Tuesday. My name is John Barris, and I'll be talking about Cloud TPUs. You can ask questions anytime on the platform, and we have Googlers on standby to answer them. So today I'll be joined by Zach Stone, the product manager at TensorFlow and Cloud TPUs from the Google Brain team. So I want to talk a little bit about machine learning and Cloud TPUs and new opportunities that are available now due to machine learning, and also the central computational challenge related to machine learning and what we're doing about it. So I have a couple of examples I'd like to mention first. You know, digital cameras were created 40 to 45 years ago. And then about 20 years ago, they became popular even for consumers. And if you had a digital camera 20 years ago, you might have been taking pictures, taking the memory card out of the camera and sticking it in your computer and just saving the pictures on your hard drive. And if you wanted to find a picture from an event or of a particular person, you had to kind of either have good organizational skills of how to keep track of photos on your computer, or you could remember when the picture was taken, kind of search by date and try to find that photo. Well, things have changed a lot nowadays. I keep my pictures on Google Photos, and if I want to find, for instance, a picture of the Golden Gate Bridge or the Eiffel Tower, I can just type in Golden Gate Bridge or Eiffel Tower into the search bar. And because Google Photos has used machine learning tools to identify objects in those photos, it can call up all the pictures that I've taken of the Golden Gate Bridge or the Eiffel Tower and present them to me so that I can go through them very quickly. It's made my life so much easier. In fact, if I have a friend that I'd like to find a picture of, if I've already tagged that friend in one photo, I can easily find that friend in many other photos as well. So that's super convenient. So that's an example of how consumers can save time using machine learning. But perhaps you'd be interested in another example that is good for enterprises. And I'm thinking about automobile manufacturing lines. It turns out that when an automobile manufacturing line goes down, it costs about $22,000 a minute in lost revenue or in costs, and that's more than $1 million an hour. And so having a machine fail on that manufacturing line is actually quite expensive. And so it's much better if the company can identify when the machine might fail and then schedule a maintenance repair to that machine during a time when the line is down already for maintenance. And so what a company might do in that case is fit those machines with sensors, maybe audio sensors, pressure, temperature, vibration, or anything like that, and then look at that data and use machine learning and use the computers to identify patterns in that data that might indicate when a machine might be ready for maintenance. And by doing that, they can schedule the maintenance on the machine instead of having the machine fail at an inopportune time. So here's some other examples too. For instance, the Google Arts and Culture app that runs on your phone can use a selfie and identify a picture or a drawing by a famous artist that most closely matches your selfie. So our colleague Satish did this here, and it turns out he looked most like Chuck Berry in this drawing by Gilbert Shelton. There's another example that's very useful when you're traveling. If you're in a foreign country and you can't read the language that's presented on a street sign or a menu, you can actually use the camera to take a picture of that menu, and then Google uses machine learning to identify the text, convert that text to machine-readable format, convert it then to a language we understand, and insert that language in the text that we can read in the same place on the image, so that we can read a menu even in a foreign language. It's incredibly convenient. Now here's another example of making life easier is Smart Reply in Inbox, where when a piece of mail comes in, instead of having to type with your thumbs the whole response, Smart Reply offers a few responses that might be appropriate for this message. And you can just press a button and then that response is inserted into the email. Then you can add your own comments and send it off. It's a nice time saver. Now, it turns out that making all this machine learning work effectively and quickly requires a substantial amount of computation power because of the increasing complexity of machine learning models that are in use. So for instance, image recognition and object detection models that are run for on images often have 50 or 100 or even more layers and billions of neurons that can be activated by the information coming in to the model. So in this example, you can see the input layer at the bottom. Perhaps that input layer is taking the data from the machines that have been instrumented in the manufacturing line. And neurons are activated based on the input data, and then that information activates additional neurons in layers above that until finally the final output layer might only have two settings, either needs maintenance soon or doesn't need maintenance soon. And so that's an example of kind of how the neurons work in a machine learning model. Now, what we're finding is that current solutions haven't provided enterprises with enough computing power, and recent AI advances are almost all attributable to advances in compute power. And in fact, we surveyed attendees at a recent TensorFlow event and found that most of them felt like their compute power was inadequate. They needed much more computational power. So our mission at Google is to democratize AI, make it available both through services and infrastructure, making it accessible, fast, and useful for enterprises and developers. We have over 10,000 customers taking advantage of our AI solutions. We've launched 12 products last year with dozens of features related to AI. And we have over 30 cloud AI partners. And in fact, we have over 1 million Kaggle members that are using AI on our platform. So now here to tell you more about Cloud TPUs is Zach Stone. Zach?
Thanks, John. Hi, everyone. I'm really excited to talk to you today about Cloud TPUs. As you can see here, this Cloud TPU board is the latest offering in Google Cloud, and it's Google's second generation machine learning accelerator. So as a product manager for TensorFlow, one thing that John mentioned earlier is that most TensorFlow users who are working with state-of-the-art deep neural networks are hungry for more compute. And TensorFlow, it's open source, it's free, it runs across a huge variety of different platforms, from state-of-the-art CPUs to GPUs to Cloud TPUs and on to mobile and embedded devices. So across all those devices, we're committed to TensorFlow providing fantastic performance. Today, we're focusing on this Cloud TPU, this new addition to the lineup in Google Cloud. So what's special about this second generation TPU? Well, first of all, on the reference workloads that we've open sourced, this provides differentiated performance per dollar. We think this is a really economical way to get work done, especially on some of these incredibly intense computational challenges associated with state-of-the-art machine learning systems. Each board delivers up to 180 teraflops per device, which is a lot if you've ever built a system yourself. And by hosting these in cloud, you can scale up and scale down easily as your needs change, instead of having to put in the capital and expertise and data center cooling and power and so forth to build a cluster like this and manage it yourself. Right now, these Cloud TPUs are architected for TensorFlow, so you can program them with TensorFlow's high-level APIs instead of having to do bespoke supercomputer programming as you might have in a previous era. Let me tell you a little bit more about the motivation behind these Cloud TPUs. First of all, it's really important to be able to train and run complex machine learning models faster. As John mentioned, one of the trends that we've observed over the past several decades, really, but especially over the past 5 years, is that increasing computational power and scale of these models has led to much higher accuracy and unlocked new applications that just wouldn't have been feasible previously. Also, we find that it's really important here at Google and elsewhere across the world to improve the productivity of machine learning teams. When you are training a machine learning model, it's common to wait for hours or days, or even in some cases weeks, for the model to converge and be ready to deploy in production. That's like waiting weeks for your code to compile. And so what we're trying to do, both with TensorFlow across all platforms and then with Cloud TPUs, is to reduce that time to hours and perhaps someday to minutes, so people can iterate faster and be more productive. Finally, as I mentioned earlier, it's really valuable to be able to scale up and down easily with on-demand machine learning infrastructure in the cloud. You don't have to fight with provisioning machines, configuring drivers. You can just connect your virtual machine to a Cloud TPU, start running open source TensorFlow, and train faster than ever before. Let me say a little bit more about ML teams of ML engineers, ML researchers, data scientists. One thing that you're probably aware, as we certainly are here, is that the talent to build these state-of-the-art machine learning models is in very high demand right now and very scarce. And so it's really important for the people that you have in your organization who have the strongest expertise in this domain to be able to move as quickly as possible. And so with these higher performance accelerators and great high-level software on top of them, you can enable your ML teams to accomplish a lot more than they could otherwise. Furthermore, I'd like to emphasize, as I mentioned before, that this is now the second in a whole line of machine learning accelerators that Google has developed in-house. We had our first generation tensor processing unit that was optimized for inference and used internally. This is the second generation tensor processing unit built into a Cloud TPU board and even into larger systems that I'll tell you about in a minute. So every time you run a search, your search results are ranked in conjunction with some of these tensor processing units here at Google. When you use Google Photos, as John mentioned earlier, some of the organization of those photos is facilitated with these tensor processing units. And across many other Google products, you're interacting with these accelerators every day, and now you have the opportunity to incorporate the same accelerators into your own businesses through Google Cloud. One thing that we're trying to do is to make it easy for people to get started with Cloud TPUs. And the way that we're approaching that is by open sourcing reference workloads that are optimized and ready to go on these Cloud TPUs. Initially, we've concentrated on a few categories of reference workloads. On visual recognition, so image classification, these are models like ResNet 50 or Inception, or for lower resource devices, MobileNet and SqueezeNet. And this is really useful if you have an object sort of centered in a frame, you know where you're looking and you need to tell, is this a cat or is it a dog? Is this a vehicle in this close crop of an image, or is it pavement, right, for an autonomous driving application? So we have a lot of models there that are ready to go, well optimized, and we're continuing to improve their performance further over time. Secondly, we've got reference models in machine translation and language modeling. These are built around this state-of-the-art transformer model that's part of the open source Tensor to Tensor library. And transformer has been really useful for both machine translation from one language to another, also for language modeling, where you're trying to predict the next word in a sentence, as you might if you're building a messaging app and you want to make it easier for people to input messages to one another. But transformer is actually more general and useful for other sequence-to-sequence problems as well. Finally, related to the small image visual classification I mentioned earlier, we've got a reference model for object detection called RetinaNet. So this is useful if you don't have a small crop, but instead you're searching for small objects in a large field of view, like you might for autonomous driving, but also for medical imaging. You might need to look for regions of an image that a medical practitioner should focus on in a large scan that may be many megapixels. And so RetinaNet might be a useful starting point if you're interested in those sorts of applications. Just to give you a sense of how broad the application domains are, even with these building blocks of these reference workloads that I mentioned earlier, I'd like to call out a few other applications. One that's quite surprising is genetic variant calling. So when you're sequencing a genome, there's this final step when you're reconstructing the sequence where you need to call variants. You need to decide, okay, the reads are suggesting that there's a base pair modified here. Is that base pair really modified or not? Is this a real variant or not? And so a team here at Google has developed an algorithm called deep variant that recasts this problem that traditionally takes hours or days on a cluster of CPUs as an image recognition problem that you can now run on these state-of-the-art machine learning accelerators, whether GPUs or TPUs. And so we think this dramatically speeds up the process, and we think this will make genetic sequencing faster and a lot more affordable to be used in many new ways. As I mentioned before, autonomous vehicles are a really important domain for visual recognition and object detection. And there are many aspects to that problem. There's some teams that are considering running machine perception on vehicles, detecting pedestrians and street signs and road markings and obstacles and so forth. Those are all visual perception problems. But also, visual recognition and processing is valuable for the mapping that often goes on beforehand. Before the vehicles even go out on the road, you need to understand the world in great detail so they have an accurate map of where they can drive and not drive. And finally, obviously, there's a huge amount of opportunity in retail. Retailers everywhere are experimenting with new kinds of customer experiences, checkout experiences, in-store experiences, shopping experiences online. And all of these experiences tend to be highly visual and require detailed understanding of what's present in an image, in a scene, in a live video stream. And so we think these state-of-the-art Cloud TPUs are going to be helpful for rapid prototyping and then deployment of these new retail experiences. So I mentioned earlier that these Cloud TPUs on the left are the ones that are available today in beta in Google Cloud, but they're also designed to be connected together into even larger systems, like the TPU pod that you can see over on the right. Now, these pods are amazing. This has a total of 256 of these TPU chips, 64 boards, and can deliver up to 11.5 petaflops of computing performance for a single machine learning problem. If you want to train a model in half an hour instead of in days. And these are coming to cloud later this year. We think these Cloud TPU pods are going to provide a great solution for folks who are starting their development now on Cloud TPUs with no code changes to then scale up by more than an order of magnitude without any code changes as long as you can tolerate larger batch sizes. So one thing that we've announced recently is that our own internal experiments have shown that you can take a model that would train in about a day on one of these boards in a certain configuration and scale that all the way down to 30 minutes training on a Cloud TPU pod. And we're continuing to optimize these systems further. So we're looking forward to bringing these to Google Cloud so you can enjoy them as well. So if you want to get started, since demand is intense, we ask that you visit the page here, cloud.google.com/TPU, and request quota. And we're doing our best to process those quota requests as quickly as we can. Thank you very much. We'll be taking questions in just a moment. We'll be right back after a minute break. Thanks again.
Welcome back. We have a few questions we'd like to answer, so we'll mention the question then give the answer. First of all, someone said, I've applied for TPU quota during alpha and again at beta, and I haven't heard anything. When will I get a chance to try Cloud TPUs? Well, I have to say they've been very popular. We just ask for your patience. You'll get a chance soon, but thanks for your patience and waiting.
Totally. Again, we wish we could give these to everyone right now, so we're trying as hard as we can. There's a second question here. I saw an article indicating the cost of training on TPUs is much more expensive compared to NVIDIA Volta GPUs. So while we won't make direct comparisons today, one thing that we'd encourage you when you get access to Cloud TPUs is to run benchmarks yourself on your own workloads. It's actually really subtle to run a benchmark accurately. You need to decide, are you processing real data and measuring the full performance of your input pipeline? Are you running on synthetic data? Are you testing that the model converges all the way to the right accuracy, as we do with our reference workloads? Or are you just looking at the step time performance? We're pretty confident that we offer differentiated performance per dollar for our reference workloads. And we're already starting to see some of our early users running their own benchmarks and talking about them online. So the performance will definitely be different from one workload to another. And it's really important for you to run your own experiments to decide what accelerator works for you. The important thing to recognize is that Google Cloud's goal is to offer the best experience for machine learning across all workloads. And that means we're hosting the state-of-the-art CPUs, state-of-the-art GPUs, and state-of-the-art Cloud TPUs. So we don't want this to be an either-or kind of a thing. You should be able to test on all of the state-of-the-art machine learning platforms, and on a workload-by-workload basis, figure out which ones are most appropriate for you.
OK, the next question is, can I use PyTorch, Caffe, or other frameworks for programming TPUs? So today, we offer TensorFlow for programming TPUs. And that's So that's the only thing that's available right now. We've heard people request PyTorch and Caffe. We don't have a solution for you today, but I'd say stay in tune, and if we have anything to offer, we'll let you know. But today it's TensorFlow only.
Great. There's a question here. Can I do inference on TPUs or only training? So that's a great question. So TPUs support training and inference. At the moment in beta, the best support is we spent a lot of time optimizing training. We've also got some early support for batch inference. If you have some huge corpus of images, let's say, that you need to process with a trained model, that's something you can do today. We are working on more optimizations over time to support low latency inference, but we wouldn't recommend that right now in production.
OK, the next question is, this is a second generation of TPU, as Zach mentioned earlier. Will there be a third generation, and can you tell us anything about it? Well, Google Cloud has not announced anything about future generations of TPUs, so we don't have anything to say about that right now.
Right. All I can comment is that, broadly speaking, hardware architecture is interesting again. So there's a whole variety of new hardware platforms that are becoming available, both here and elsewhere. Let's see if we have any other questions.
Yeah, we don't have any other questions, so stay tuned for the next session. Showcase your data stories online with Google Data Studio.
Thanks for tuning in. We appreciate it.